You good? All right, we're going to get started. So welcome. This is a technical session. I'm going to give a brief overview of intersection validation, work that's been going on with a collaboration of a couple of organizations. So SCMS Manager is one. I'm Brian Romansky. I'm the chair of SCMS Manager. I'm also the general manager of V2X systems at ISS. So SCMS Manager is a policy authority for North America. We run the certificate trust list that allows SCMS operators to interoperate and to work with devices across all of North America. We're founded by a group of OEMs and a growing number of industry partners. And as an OEM-initiated organization, we try to bring a balanced view of the OEMs and the rest of the community, the rest of the industry. As you'll see, intersection validation is one area where that interface is particularly interesting and fraught with some questions. So we're going to talk a little bit about what are the challenges with understanding the quality of the data that you get from an intersection, how that impacts the OEMs, and what we're doing about it collectively. It's not really covered in the slides. I'll just mention that this work was done not solely by SCMS Manager. It's in collaboration with a SMART grant. So Utah Department of Transportation has a federal funded SMART grant to actually exercise and implement some intersection validation. There's also some work from CAMP, so the Crash Avoidance Metrics Partnership, an organization that did a lot of the early development work of SCMS. They've been involved in this as well, helping develop some of the tooling. There's a few other contractors who have been helping out along the way, but those are the main organizations along with SCMS Manager. With that, so one of the challenges that I think some of you are familiar with is that traffic cabinets were never really intended to be connected to the outside world, right? So historically, any traffic control devices existed in a purely isolated offline environment, and maybe they were connected to a local transportation network, but nothing beyond that. So connecting them through a radio link, connecting them through the internet to other systems is a huge change for the whole industry. And a lot of the early pilot deployments for V2X demonstrated some of these challenges. One is just connectivity, but another is that getting data out of a traffic controller and into a roadside unit and getting them to collaborate and coordinate is non-trivial. There's a couple of different architectures that have been worked out to make it work, and there's ways to make it basically function. But that doesn't necessarily mean it functions well. I've heard of cases where the SPAT data being broadcast by the RSU and the actual signal head can be out of sync by as much as, say, 3 seconds. So you can watch the signal change in front of your face, but the data doesn't get updated on the SPAT message for seconds later. Or sometimes we've seen traffic controllers where, depending on which protocol you use and which data you're grabbing out of the controller, they might skip cycles, so yellow in particular. So we've seen cases where you'll see green, 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 and it just jumps straight to red, and then back to green, and it skips the yellow cycle just because, again, these are features that were never really built into the traffic controller. It was never really a safety critical thing. It was an afterthought to have this sort of serial data port that you could move data through. So this has not up to now been a critical feature. So now when you connect them to an RSU, the fact that you can make it work and you can broadcast a SPAT message that sort of kind of correlates with the traffic signal head, that's interesting, and that might be all you need if your mission is just signal priority and preemption. So in a place like Utah, their first deployment was snowplows. They get a lot of snow. They want their snowplows to be able to get through the traffic lights quickly, so they set up signal preemption, or actually still priority on their snowplows. And so signal phase and timing accuracy is really not a critical thing for them. They broadcast it, they broadcast a map message, but the most important thing is that the snowplows can broadcast an SRM, and the RSU can get back, and they can collaborate and authenticate each other. But when they start talking to OEMs, so vehicle manufacturers, and they say, we want to start making production vehicles, we want to use your roads, we want to take advantage of the investment you've made in all of this infrastructure, we also want to make sure that the data that we're getting is accurate and useful. And that's not obvious, right? If you just walk around to a traffic signal, you can see what the signal head's doing, but you don't know what the radio is doing. And if you have an OBU, you can get the radio signal, but there's no easy way to synchronize that with what you see. So making sure that the physical and the digital are aligned is actually not trivial, right? There's no existing off-the-shelf box that just does that. And so that's why a lot of these problems go hidden for a long time. Like you can set up an RSU, it can do its job for signal priority preemption. You can listen to the broadcast from it and it might be fine. But you may not realize that they're out of sync, or you may not realize that they're perfectly in sync when you set it up, but 6 months later, because somebody changed something, you change the programming in the controller and now they're out of sync and you don't realize that it's broken. So that can happen as well. So the OEMs have started to question, like, how good is this data? The fact that we've got, there was this BAT challenge 10 years ago or so. So a lot of deployments happened at the time using DSRC. Some of those have been upgraded to CV2X now. But again, with nobody checking the quality on these things, it's unclear how good that data is. And that's a question that's come up from the OEMs. And a concern they have is, if I issue false alerts to my drivers, that's almost worse than nothing at all, right? If I have a driver who gets complacent because they think this thing is going to give them some assistance or some aid, but it's unreliable, or it some works sometimes and not others, or it's way out of sync other times, like that's not a useful safety feature. You're better off without it than to try to introduce this thing. So that's the challenge that they have for the industry is prove to us that this data is accurate. So that's the question then. How do you make sure that V2I data are accurate? How do you make sure that they're calibrated and correct? I also want to mention, obviously we're here at a Plugfest. OmniAir has invested a lot in test plans and certification. What we're talking about here is not questioning the value of that certification. So a certified device is a device that's proven to work correctly, right? You've run it through all the paces, you run it through a set of test cases, you validated that input-output correlations are correct, the messages are formatted correctly, they're signed correctly. So you've checked the box and all the surrounding materials around this RSU, this unit. That's great, and that's really valuable, and that's a critical element to making this work. It takes care of a lot of open questions that, hey, this box works correctly, that's good to know. Problem is, I take that working box and I put it into a traffic cabinet. Now it's part of a much broader system, and it's dependent on the traffic controller programming, the protocol that the traffic controller uses, the bus between the traffic controller and the RSU. You might have a translation layer in between, a V2X hub, or a connection layer that's might be a Raspberry Pi, or it might be a hardened box. There's many variations of these interface boxes that have been developed and built just to connect traffic controllers to RSUs. Those aren't part of the certification plan right now. Those are a whole separate entity that is just providing connectivity. So there's no way to know exactly what it's doing or how much latency it's introducing. We have standards. We have CTI 4501 and NTCIP 1218. These standards do define performance requirements. They do define the expectations of the boundaries of the traffic cabinet, how it's maintained, how it's secured. But again, they don't necessarily tell you how to do the testing. So they don't tell you what do you do in the field to make sure that your system, once it's installed and deployed, is actually working correctly. So they get you partway there, and they're very useful to help put some bounds on the metrics of what you're looking for, but they don't tell you how to do an actual validation or how to enforce it over time. When I talk about intersection validation, what I'm really trying to get at is a validation that you're actually compliant with the standards. And even more narrowly defined than that, really what I'm going to talk about is red light violation warning. So the standards, particularly like 4501, has an extensive number of requirements on a traffic cabinet, on an intersection. And trying to validate and prove every one of them would be exhaustive and extremely time consuming and extremely expensive. So we tried to narrow the scope to say, well, let's pick a safety critical use case that actually is important. It's important to the OEMs, and it should be supported by a basic, most intersections that are sending out SPAT and NAP should be able to do red light violation warning at a bare minimum. There's many other more advanced safety features that you could do, But as a starting point, let's make sure that they're good enough, the data is good enough for that. And that helps narrow down the scope a lot. So it helps you rule out a lot of the requirements in 4501 to say they're all important, and we're not telling you not to ignore them. We're just saying, here's the subset of 4501 that we're actually going to test and measure and make sure that it's validated compliant. The other thing is we recognize that there's sort of two things going on here. There's a point in time validation. So I can go to an intersection, I can plug in equipment, I can take a bunch of data and measurements and prove that everything's working correctly. But as I said before, I might come back 6 months later and realize, oh, they repaved the paint lines, or they reprogrammed the controller, or I didn't account for the fact that the controller goes through multiple cycles at different times a day, and sometimes it works great and other times it doesn't. So we've introduced this notion of what we call continuous monitoring to say, it's great to do an initial validation to say, hey, your intersection is good at this point in time, it started off okay, but can we check to make sure that it continues to work correctly, or that it's plausible that it's working correctly? So I'm going to talk about these two procedures in a bit more detail. So the initial validation is that process of I installed a new intersection, I connected it to my traffic controller, I'm going to take some measurements comparing the physical changes of the signal heads and the SPAT messages that are being broadcast. I'm also going to check that the map messages are accurate. And again, when we started this process, it wasn't at all obvious how to do that, right? So just getting accurate data out of the signal cabinet as to what is the traffic light actually doing right now, and comparing that against the broadcast data, not obvious. Or again, there's not a lot of equipment you can buy to do that. This is where a team at camp had put together some technology. They took an OBU that can receive the V2X messages over the air. They can connect to the SDLC bus in the cabinet, which gives you very accurate real-time data on what the relays in the traffic cabinet are doing. But then they had to do the work of like figuring out how much time lag is in there. So when RS or an OBU receives a broadcast message and validates it and does some processing on it, there's some time lag in that, and then there's also some time lag in getting the serial data from the controller and trying to make sure that, okay, how much default delay is in my processing, so that physically, like, how aligned are they? If I'm going to be doing a calibration or a measurement on this, I need to know how good my tool is. So they spend a lot of time doing statistical analysis to show that, yeah, this OBU with this software and the serial bus adapter, they know what the synchronization offset is, so they can resync them, and in the data domain actually know like how closely aligned are these two things. In the physical world, understanding are your map points accurate? So many of you know most map data in North America today, and probably the rest of the world, is based on satellite imagery. So you take Google Maps or Bing Maps or somebody's satellite image, and you start picking points that are sort of approximately where the lane lines are, the lane center points are, and you build a map message. And that alone is pretty tedious to do. There's a lot of points you got to pick, a lot of coordination of which lanes connect to which lanes, and the flow of traffic. And so encoding all that data is fairly tedious. Worrying about how accurate those points are up to now has not been a high priority. People kind of make their best estimate, zoom in as best as they can, and they assume, huge assumption, that the satellite data is actually aligned with ground truth, that the GPS coordinates you get off of those pixels on the satellite are really correlated with physical real-world geometry coordinates on the ground and where the paint lines are. So we recognize that there's a huge set of assumptions there, and the map data that you get may not always be accurate. So now when I'm trying to position a car in a lane using GPS data against this human picked off of pixels map data, I might not be in the right lane. I might sometimes, especially if I'm off by half a meter or something like that, and the car GPS is off by half a meter in the other direction, very easy to put yourself in the wrong lane. So how accurate can you get? We've done a bunch of work and found that LiDAR data seems to be the most accurate way to get fast data that you can use to validate these maps. So with a LiDAR scan of an intersection, you can actually figure out exactly where the paint lines are. So working with a couple of vendors, the team at Utah has worked out a couple of scripts where they can take extremely dense, extremely complex LiDAR data that gives you sort of 3D topology of the whole surface of the road and color at every pixel. And then they can actually pick out where the paint lines are and identify the exact zero or center line of all the lane lines. and have something that's much, much more accurate than, say, 20 centimeters. So the goal here, and what 4501 says, is that your map point should be within a 20 centimeter bounding box of the real physical location. So it's not a very big box, and again, if you're picking from a satellite image, trying to get that accurate is pretty hard. So we've invested a lot in this whole processing process of saying, okay, can I get the LiDAR data, process the LiDAR data, get the ground truth of where the paint lines are, compare that to my map data, know how far off my lines are. They also put together some tools that will look at things like periodicity and content of the spat and map. So again, we see some intersections where the spat data, it's supposed to be every 100 milliseconds, but sometimes it might get delayed because the RSU is busy doing something else, or you might just have substantial jitter in terms of the periodicity of that data, which for, again, a routine use case like signal priority and preemption may not be a big deal. But if a car is approaching at speed and dependent on up-to-date information on what's happening, that could be a problem, right? You want to make sure that there's a reason why that 100 millisecond data update is intended to be there. So we have another tool where you can take a PCAP of over-the-air broadcast data of spat and nap from an intersection, run it through analysis, and it'll tell you, are all the critical data elements, required data elements present, and is the periodicity correct based on the timestamp in the data. So that is all the initial validation. You can't take your LiDAR data and make sure that your map points are accurate to the paint lines. You take physical, connect to the traffic controller, to the SDLC bus, compare that to what's broadcast to make sure that the spat data is accurate and timely. And then you also run this analysis on your PCAP to make sure that the content and periodicity of your data is accurate. If you do all of that, you can put together a report that says, yes, I've done all these checks, we've passed all the 4501 requirements that are critical for red light violation warning, we've got a good intersection at this point in time. Oh, and by the way, you don't just do that at one point in time, you want to do it throughout the day because, again, traffic controllers will have different timing cycles based on traffic patterns and times of day. So you want to make sure, like, if there's a walk signal, that you can shift the timing for a pedestrian, if there's other preemption priority modes or different times of day. So you want to make sure you check all of the different conditions because, again, there's no guarantee that because the system works in one condition that it works in all the others. Once you've done all that, then you switch into what we call continuous monitoring. So the idea here is, what's a practical, efficient way to continuously capture data and compare what's physically going on in the real world and how that compares against the digital data. The approach that we've focused on for now is SCMS, this Connected Intersection Message Monitoring application. This is an application that was developed, it was funded through the Pooled Fund Study, so a group of DOTs in North America have brought together their funding to fund these individual projects. SCMS is one of the things that came out of that. So what SCMS does is it collects BSM data received through RSU. So an RSU forwards the BSM data to a cloud instance or a local instance of the SCMS application. And it does plausibility estimates. So it says, I see paths of a car driving through the intersection. I know that some drivers are careless or lazy or distracted, so they're going to do weird things. So I know some drivers are going to do things maybe unexpected. But I expect most drivers to follow the lanes correctly. I expect most drivers to follow the traffic signals more or less accurately. So I'm looking for plausibility. Like, if I see a whole stream of cars that are running through a red light without ever slowing down, it's probably a sign that it's not really a red light. Maybe the spat data is telling me it's red, but it really isn't. Or if I see cars that are driving backwards to the intersection, or they're making paths that really aren't legitimate connecting paths for the intersection, it's probably a sign my map data is wrong, not that the drivers have all gone crazy, right? So SCMS can collect this data, run an analysis, and come out with a plausibility estimate to say, how credible is this data based on what the spat and nap information is telling me at this point in time and what I see cars actually doing. And one limitation of this, of course, is SCMS only works well when you have a lot of cars going through the intersection, right? If I have one police car in my whole town that's enabled with V2X and I only get it once a day, that's not very useful, right? So this works reasonably well if I have a whole fleet of buses and other fleet vehicles in my municipality that are connected. I can get enough data that this starts to be useful. If it's very sparse, then it's not very practical because I'm just getting that one driver. So this is sort of a sense of how this process is intended to work. I'll walk you through it at a high level. So you start up in the top right of I create a new intersection, I install it, and I decide this is going to be a validated intersection. One thing to recognize is that the claim here is not that every intersection everywhere in the world needs to go through this whole process. The idea is you'd start with the ones that are most safety critical. So if I have intersections where I have a lot of accidents, or I have intersections where there's a lot of people running lights, or I have higher concern about them, I might start there and validate those first so that vehicles can use this data once they're enabled. So I'm going to pick which intersections I want to have validated. I contact an SCMS provider. So my certificate provider is going to help me. They're the oversight to make sure that this process is working correctly and that all of the pieces, they're the mediator between the OEM and the IOO. So the SCMS provider are going to collect information about all of this process that's happening, make sure it's all on file, make sure it's all correct, and issue the certificates and the credentials that allow vehicles to trust that this data is actually accurate. So as an IOO, you set up your intersection, you contact an SCMS provider, and you say, hey, this intersection is going to be validated. It's not yet, I just turned it on for the first time, or I'm about to turn it on. Please give me a certificate, a production certificate, so I can turn it on and start to collect data. So you start off in this unvalidated state, you get an initial production certificate, but at this point you're still unvalidated, and I'll show you how you indicate that in a second. You start off in an unvalidated state, you run your measurements, you put together a report that shows all those things I went through. Your map data is good, your spat data is accurate, your content is correct. You submit this electronic machine readable report to your SCMS provider. They automatically process it, say, yep, everything looks good, and then they will start to issue certificates that allow you to show that you're validated. So you move into this validated mode. That's where continuous monitoring cuts in. So a tool like SIMS or some other continuous monitoring tool is going to be collecting data and submitting a report periodically to your SCMS provider to say, yep, I'm checking it, everything looks good at this intersection, no problems. As long as that's the case, you continue in this sort of system okay mode of I stay validated, everything's fine, there's no issues. If a report doesn't show up, meaning the monitoring has stopped working, or you get a report that says things don't look aligned anymore, I see enough statistical variation in what drivers are doing that it doesn't look like the spat data is accurate anymore, then you can go into a suspend state. So you can actually send a message to the RSU that says, I don't think you're reliable anymore. Stop telling cars that you're validated. And so I'll show you in a second how they can make that change. And if this continues, if they don't correct the situation, if the IOO isn't responsive to making sure the data is accurate and valid, then eventually they can become suspended, meaning their certificates are going to switch back to this unvalidated state so that you can't be lazy about it. You can't claim you're going to be validated, get the special certificate, and then just ignore it. Like you have to be on top of it and keeping track of this stuff. So there's two bits of information that help relay the signal status or the intersection status to a vehicle. One part is attached to the certificate. There's an SSP bit that we've requested from the CTI 4501 group that is going to indicate, hey, this is intended to be a validated intersection. So that SSP bit will get issued when you make that request to say, I want this intersection to be validated. Now, one thing that's kind of cool is, as some of you know, right, when you go to an SCMS provider, you enroll your device, they're going to issue application certificates to you. The SCMS provider can actually change what's in those certificates over time. So the idea here is that initially you get certificates with that SSP missing or that bit turned off to say, you're not yet validated, so you can't claim to be. Once a report is on file and they've confirmed that your initial validation looks good, then the next application certificate that you download, which you download weekly for most RSUs, the next application cert is going to say, hey, you're now validated. That bit will be present. So you have this sort of slow acting response mechanism where over a week's period of time, you can switch from being unvalidated to the next batch of certificates show that you're validated, or vice versa. If you're not behaving correctly, if the IOO is not responsive and not keeping their equipment calibrated, you can take that away, and a week later, that SSP will go away. So it's a slow mechanism of enforcement. It takes about a week for the next certificate to get issued and into the system. But it's a way of enforcement to make sure that an IOO that's not being careful and not managing their equipment can be taken out of the system so vehicles aren't falsely convinced that they should trust this intersection. But it's a way to provide a level of enforcement. There's also a faster route. There's a bit that's going to be in the SPAT data itself that actually shows I'm currently operating in a compliant mode. I'm currently compliant with all the 4501 requirements. We've reached out to the 1218 groups. The 1218 standard talks about interfaces for the RSU, the inputs and outputs. And they were already planning to have feedback so that you could tell an RSU to go into standby mode if there was a problem with it, if there's known to be an issue with the intersection. So we're requested a special message that can tell the RSU, hey, there's a problem detected through continuous monitoring. Flip off this bit so that you're no longer claiming to be validated. And that can happen in an instant, right? That can be very quick. So a good example is if I see a SPAT message that shows that all lights are green in all directions, right? That should never happen, right? The traffic controller should never let that happen. The RSU should never let that happen. That's a message that should never be broadcast. But technically it could. Like you can form a SPAT message that says all lights are green in all directions. So SIMs would immediately see that and say, clearly there's something horribly wrong with this intersection. That's probably not what's physically happening at the traffic light. Don't claim you're validated anymore. So this message would come back, that bit would get flipped. Cars approaching that intersection would be informed that it's no longer operating in a compliant, validated mode until the IOO does something to correct it. They got to send somebody out. They've got to do something. There's actually a policy, a draft policy that we worked on in SCMS Manager where we go through all of the alerts that SIMs can produce and identify like what's the recovery. So there's some that are pretty blatant, like I said, messages that should never happen, immediately go into standby mode and send somebody out and figure out what's going on, do a root cause analysis. There's others where it might be, you know what, it's just a statistical trigger. So like knowing where the stop line is. Some cars will stop before the stop line, some will stop after. You might want to just tweak the statistics. If you're getting a lot of alerts that say, the stop line location looks wrong, it might just be that you need to relax the filtering a little bit. So there's some where we're a little more, use your judgment to say what looks right and what isn't. And others that are, this should never happen, stop immediately. Just to go a little more into detail, if you're familiar with J2735, it defines the structure of all of the messages. If you dig into the SPAT message, there's an element in your SPAT. That's the intersection status object. It gives you status information about the intersection. We've looked at a couple of different bits in there. There's a bit called no valid SPAT available at this time. That looks attractive because it's kind of overlaps what we're trying to say with this new bit, this new meaning. So one suggestion is maybe just relabel and redefine that bit and say this really is the validated intersection bit. Although we've gotten a little bit of pushback because I guess there are a couple of deployments where they may be using that for other purposes. There's two reserved bits 14 and 15 were initially reserved. So the thought is we could pick one of those. So again, this would be through the, I guess the 4501 work group will decide, sort of, go through their balloting process and decide which bit do they want to allocate to become the real-time SPAT information bit. Note that we're looking at the SPAT message, and I'm talking about SPAT, but the bit actually covers the whole intersection. What I mean by that is there's SPAT map, and we've also looked at RTCM for the real-time corrections on the GPS coordinates. So this bit being said, if it says it's validated and it's compliant, it means that all of those messages are currently validated and compliant, right? Your map is good, your SPAT is good, and your RTCM is present if it's required. But we decided just a single bit makes sense. Having separate bits to say, well, my SPAT's good, but my map's bad, or some other combination, just too confusing for the receiver to try to make sense out of that. So we said, it's a single bit. It says, my intersection is good. Put it in the SPAT message, and this is your real-time way to know things are good. Okay, and so we've done a lot of work on this. The plan is we're working now to set this up and to do a field demonstration. So if everything works out, we'll have some equipment to show you tomorrow. We will have basically the equipment that does the initial validation. So there's a Pelican case with some boxes in it that will connect over at intersection number 1 on the track here. If everything goes well, we'll be able to actually show some data. So we'll do some data collection, show the report that it generates, and give you a sense of like the graphs and the views. The report was intended to be instructive. So if you're setting up a new intersection and you're not passing the validation test, like, well, what's going wrong and what do you need to do to fix it? I will say we worked with Utah for most of this past year. They've got about a dozen intersections that they've been working on. Not a single one of them have passed all of the requirements yet. So they have not yet gotten to a point where they have a validated intersection. It's hard because, again, the traffic controllers are never built to do this. We're trying to apply fairly stringent standards on timing and periodicity and data accuracy and latency. So trying to maintain that is actually quite difficult. So until there's a new generation of traffic controllers and RSUs that really are built to do V2X from scratch, I think it's going to continue to be hard. I think in the future it'll be way easier, but today it's still a challenge. And we'll also be able to show, again, if all goes well, continuous monitoring. So we've got an instance of SIMS up and running. There's a browser page that you can go to sort of see what's going on. So it'll show you if there's any alerts. So if we drive a car like backwards through the intersection or through some implausible connection of lanes, you should see it right away. It throws an alert to say that shouldn't happen, and this is what I saw and when it happened. So there's like a breadcrumb of BSMs that it shows, and you can actually look at like what the vehicle did. Not sure we'll have all of that working, but hopefully we can at least show that SIMS is there and we're getting data from it and it's working. So we'll try to have it set up. So hopefully we can show you a couple of those things tomorrow. I hope this gave you some sense of what intersection validation is about and why it's important, and that it's really hard. I mean, there's a lot of equipment, a lot of planning, a lot of integration that has to be done to do this. Trying to make it work across all types of intersections, because there's many different types of cabinets in use in North America, different types of controllers, different serial buses. So it's hard to make a consistent, uniform solution, but we're trying to get there and trying to adapt the policy to make this something that OEMs can integrate into their logic so that they know which intersections they can trust and actually alert drivers on, and which ones they should say, it's informative information, but probably not something alert worthy. With that, I'll spare a few minutes. Any questions?
Excellent presentation. Thanks. Just a quick question. The tools that are being developed, those are being developed by the full fund study. I assume those will be open source available in it.
Yeah. Yeah. Everything that's built as part of this project, will be open source. So the pooled fund study will publish a report. It may already be on their site. That is like a phase 1 final report. So all of their findings and all of the analysis tools are available. All of the the data capture stuff. Like there's a hardware you have to buy. So they have some loaner units if you want to borrow one just for experimentation. But you could build your own and you could get all the code. And I mean, most of the analysis is either Python code or it's an Excel spreadsheet. It's kind of cobbled together with different bits and pieces. At ISS, we've done a little bit of work. So like the PCAP analysis, we have a utility built into our platform that you can run the PCAP analysis. And so you don't need to install anything. You just run it from our platform. So I expect you'll see other commercial implementations like that. Some of the vendors who do deployments or vendors who do intersection support will start to incorporate these things. So it'll get easier over time, and there'll be a lot more built in that you just get out of the box. Like SIMS, for example, is a tool that's getting some popularity. So I think most of the intersection monitoring or intersection management systems are considering or currently have SIMS built in as a feature, so it can be hosted. Any other questions? Hopefully we'll have a demo to show tomorrow. We're still doing some integration, so we'll let you know in the morning where that's at, and see you there. Thanks.